In this lesson on capacitors, we will discuss what capacitance is and what a capacitor is made of. We will state the units of capacitance and examine how capacitors act in a direct current or DC circuit. We will also take a quick look at capacitors in alternating current or AC circuits. However, capacitance in AC circuits is fully covered in the lessons on AC. A capacitor is a device that stores electrical energy in the electrical field that can be created between two conductors that are separated by an insulator. In its simplest form, a capacitor consists of two metal plates separated by an insulating material called a dielectric. Wires connected to the plates allow the capacitor to be connected into an electrical circuit. If we connect one plate to the positive terminal of the power source and the other to the negative, electrons will flow to the plate attached to the negative terminal and will be drawn from the plate attached to the positive terminal. There will be no flow across the insulator, but one plate will become negatively charged with extra electrons, and the other positively charged because of a shortfall of electrons. The attraction between the oppositely charged plates will produce an electrical field across the dielectric. In this electrical field, the electrons in each atom of the dielectric are attracted to the positive charge and repelled by the negative charge in the manner shown. However, they are too firmly attached to the nucleus for any to escape. Once the charge voltage across the plates equals the supply voltage, the flow of electrons will stop. If the capacitor is now removed from the supply, it will retain this charge until it is connected to an external circuit. When the surplus electrons on one plate will flow through to replace the shortfall on the other, and the atoms in the dielectric will return to their original shape. If we place a capacitor in a direct current circuit, as shown, when the switch is placed to position A, the capacitor will be connected to the power supply. The ammeter will initially show high flow, then fall to zero. We can see from this that in a DC circuit, apart from the initial charging current, a capacitor blocks current flow. When the switch is moved to position B, the capacitor will now discharge through the resistor, and the ammeter will once again show a high flow, which will fall to zero. Much of the electrical power used on aircraft is alternating current or AC. In AC systems, the polarity of the supply voltage changes cyclically. The change happens at a much greater rate than shown here. In fact, in aircraft AC systems, it changes 400 times every second. If a capacitor is placed in an AC circuit, it will constantly be charged and discharged as the polarity of the supply changes. So electrons will constantly be flowing to and from the plates of the capacitor. Although no current flows across the capacitor, current is constantly flowing in the wires, and if a light bulb is placed in the circuit, it will remain illuminated. From this, we can deduce that a capacitor appears to allow current to flow freely in an AC circuit. Capacitance is the ability of a capacitor to store electrical charge. The unit of capacitance is the farad, F. In terms of capacitance, the farad is a very large unit. A 1 farad capacitor could be as large as a Coke can. The farad is therefore subdivided into smaller, more convenient units. 1 microfarad is 1/millionth of a farad. 1 nanofarad is 1,000th of a millionth of a farad. And 1 picofarad is 1/millionth of a millionth of a farad. Capacitors are also rated by their working voltage. This is the largest DC or peak AC voltage which can be applied across the capacitor. It is usually marked on the case of the capacitor, and if it is exceeded, the dielectric may break down, permanently damaging the capacitor. There are 3 factors that affect the capacitance of a capacitor. These are the area of the facing plates, the distance between the plates, and the material of the dielectric. It is fairly obvious that the larger the area of the plates, the more electrons can be stored on them, so capacitance will vary directly with plate area. The distance that the plates are apart determines the strength of the electrical field between them. If the plates are widely separated, the electrical field will be weak, and it will not pull many electrons onto the negative plate. If, however, the plates are very close together, the attraction caused by the unlike charges will produce a strong field, and lots of electrons will be attracted. So capacitance varies inversely with the distance between the plates. The third thing that affects capacitance is the material of the dielectric. Different dielectric materials have different effects on the electrical field, and this will give different values of capacitance. In order to compare different materials, they each have what is known as a dielectric constant, or K. The standard is air, and it has a dielectric constant, or K value, of 1. Waxed paper is a commonly used dielectric. It has a K value of about 3. So a capacitor having wax paper as its dielectric would have 3 times the capacitance of the same capacitor having air as its dielectric. Mica is another commonly used dielectric. It has a K value of about 5.5. Capacitors can be either of a fixed or variable capacitance, and they may be polarized or non-polarized. A polarized capacitor can only be used in DC circuits, and it must be connected in the correct direction in the circuit. If it is connected wrongly, it will almost certainly be damaged beyond repair. A non-polarized capacitor can be used in either DC or AC circuits, and can be connected in either direction. These are the circuit symbols for polarized and non-polarized fixed capacitors. Variable capacitors can have their capacitance varied either manually or automatically. A typical variable capacitor has a set of fixed plates and a set of rotating plates, so that the amount of overlap between the plates, and thus the capacitance, can be changed. This is the circuit symbol for a variable non-polarized capacitor. Next to it is the symbol for a preset capacitor, which can have its capacitance adjusted by maintenance personnel. Here is a summary of the electrical circuit symbols used for the various types of capacitor. Familiarize yourself with them before moving on. If capacitors are connected in parallel, they will act as one large capacitor. with the total area of the plates equal to the sum of the areas of the plates of all the parallel capacitors. Thus, the total capacitance of a number of capacitors in parallel can be found by adding together the individual capacitances. In the example here, there are 3 capacitors in parallel. The total capacitance will be C1 plus C2 plus C3. That is 1 plus 0.5 plus 0.7, which is 2.2 farads. When capacitors are connected in series, the distance between the plates is effectively increased, and therefore the total capacitance is decreased. The total capacitance is found by using the same formula that we used for resistances in parallel. So, 1 over the total capacitance is equal to 1 over capacitance 1 plus 1 over capacitance 2, and so on. In the example here, we have 3 capacitors in series. To calculate the total capacitance, we use the formula. So, 1 over the total capacitance equals 1 over 1 plus 1 over 2 plus 1 over 3, or 6 over 6 plus 3 over 6 plus 2 over 6. That is 11 over 6. The total capacitance then is 6 over 11, or 0.55 farads. In a DC circuit, a capacitor is used in much the same way as an accumulator in a hydraulic system. It stores electrical energy which can be fed back into the system when required. That is the end of the lesson. Here are the main points you should take from it. A capacitor is a device that stores electrical energy in the electrical field that can be created between 2 conductors that are separated by an insulator. In a DC circuit, apart from the initial charging current, a capacitor blocks current flow. A capacitor appears to allow current to flow freely in an AC circuit. The units of capacitance are the farad, the microfarad, the nanofarad, and the picofarad. Capacitance varies directly with plate area. Capacitance varies inversely with the distance between the plates. Different dielectric materials give different values of capacitance. Finally, the formulas for calculating the total capacitance for capacitors connected in series and in parallel are on the bottom of the screen.